This is activity ZD89, and I refer to it as a robotic arm problem. If you are referring to the chapters in the book, it's chapter 11. And in chapter 11, I have some dimensions specified, but I'm not going to bother worrying about these dimensions, okay? So I'll make my mechanism without worrying about dimensions. Of course, when you ignore dimensions later on, when you put physics into the problem, then you may get things that are not meaningful as far as the size of things is concerned. But anyway, it doesn't matter. So let me go ahead, make sure on the midterm or the final, you respect the dimensions that are given and the shapes that are given. And uh, yeah, okay. All right, let's go ahead here. Since I'm not worried about dimensions, I'm going to maximize that. Let me start with the product file. I notice that I'm not in assembly design, although things can be made here, insert part, etc. But I'd rather go to the assembly design and do it there. Okay, immediately save this thing. So file, save management, save as. Have a folder called ZD89. It's right here. So everything is going to go there. Okay. So let's do the stand first. When I say the stand, I mean this piece, okay, the vertical piece. Uh, so let's go back here. Insert a new part in there. And I'm going to call this thing right-click properties stand. Stand. Or you can call it the base if you want. Stand. All right, let's make it. Double click on a convenient plane, on this horizontal plane. I will sketch. And on purpose, because I want to do multipath, I do this kind of weird uh, sketch here, on like that. Another circle, and another circle. Exit. We'll do a multipath. So this one is the rectangle. Let me make this thing 10 millimeters. This other one, I'm going to make this thing, this is going to be the small circle. This is the bigger one. Let me make this thing 100. I will fix it if it doesn't look good. Yeah. And this one is the small circle. I'm going to make it 110. There we are. Okay. All the way to the top. Click on the floppy. Okay. Let's do link number one. Link number one is, let's call this thing. Okay. Link number one. So insert, new part, link one. It's going to be link one, or you can call it arm one if you want. Link one. Okay, let's go make it. Double click. It's very convenient to work on this plane. We sketch. Okay, so let me do the following. I will project that circle. Okay, there we are. And here's the normal view. Okay, now I do the, for example, elongated hole. I like that. I'll do elongated hole. Okay. Except that This is too big. I'll make this thing maybe 6. So it looks like, okay. And I make this thing concentric with that. So this circle control that circle, uh, concentric. Good. Okay, so maybe I may make this thing a little bit longer also. Very good. Okay, so let me draw another circle at this end. Doesn't have to be the same size, so exit. We can make a path. We make it maybe 5 millimeter. Let's see how it looks like. Yeah, that's good. All right. So what I've done here is this piece now. Okay. All right. So all the way to the top, click on the floppy. Click on the floppy, link to insert, new part, link to, and link to. Okay, let's go make it. So I'll sketch on that face. Okay. Why don't I project that circle? Okay, there we are. And then the rest of the link, just like I did it for this one. So let me make another elongated hole. I'm not sure how this thing goes. Yeah. Okay. It was a good idea to select the center of that. Okay. Now a little circle on this side. That's where the vertical pin is going to go. So exit. Now, one of them, I want it to be, this one I want it to be a pin, this one a hole. Now remember, as a mechanism, it doesn't matter. You can have hole and hole. Still it works. But it just doesn't look as good. So let me go here, multipath, this. That is the big boundary. So we made that. I'll make this thing 5. This one is the hole on this side. The little circle on this side, I want to keep it as a hole, so I'll leave it as 0. And this is the one on the left side that I want to make it a pin. So I'll make it maybe 8. There. Okay. Where's the other guy? Let me see. The other fellow is in hiding, so I can bring it back so that I can see it right there. So there is a stand, there is link 1, there is link 2, and then of course we clean it up later by making constraints. Insert, a new part, say no, and I'll make this thing a vertical member, or link 3. I'll call it vertical. Vertical member. That's the instance name, and this is the part name. Vertical member. Okay, let's make it. Double click on a convenient plane. On that plane, I will sketch. Okay, let me project that circle. Good. There's a circle. Exit and pad it symmetrically. Let's make it longer. Like that. Okay. Good. Now, all the way to the top. All the way to the top. Save everything. I have 2 choices. One choice is make this path as belonging to the stand. So I can go to that stand and somehow draw this some kind of a path on it. The other option is to insert another part, call it the path, and then move on, just like you did here. That's in several of the videos that I posted from previous years. I have actually made it out of made it to belong to the stand, but here I'm going to do that differently. So insert new part in there, no, and I'll call it the path. Right click, properties, uh, yeah, properties, path as a new part. If you're watching the videos from previous years, you'll see that I've done it differently. Path. You say, okay, now we go there and we want to make it. The only thing is that I want this path to be at an, I don't want it to be horizontal, vertical. I want it to be at an angle. So here's what I'm going to do. I'm going to draw a plane in this path. I'm in the path. I haven't done anything yet. In this part, I'm going to draw a plane that is at an angle with respect to the space. So how do you do this? First, you are in path, you create a plane. And the method of creating plane is going to be this. Maybe angle and normal to a plane. Okay? This is the way I'm going to make it. Okay. Orientation axis. In other words, this plane, I want to be able to rotate it. So this is going to be the axis of rotation. The reference to begin with, I'm going to make it lined up with this. So notice that right now, that plane is vertical, but the angle, I can change it now. So for example, I can change it. Notice that it is turning. It is turning. See that? And then we say, okay. Now I go on this plane. This is all happening within path, and sketch on it the path that I want. Okay. So I think I've taken maybe, I don't know, an ellipse or something. You can do a spline. It makes no difference. Exit. Is that good? I can make it a little bit, yeah. Notice that if you make this thing far away from this where the arm is, it can never reach it. But I'm sure this one is okay. Okay, this one is okay. Now, okay, so one more thing. At the bottom, see that at the bottom of this guy, at the bottom of this, I want to make a point. So in order for me to make a point at the bottom of this vertical link, I have to go to the vertical link. And at the bottom of, I am in vertical link now. I create a point. And the method of creating point is the circle center. So I'm going to zoom in, select that circle, and notice that it did create a point there. Why I did that is because later on I want to put this point on that path. Okay? All right. So now comes the assembly all the way to the top. All the way to the top. Click on the floppy. Well, first anchor something. I'm going to anchor the stand. So anchor the stand. Okay, good, good. Move these things apart. So let me move this thing, translate this thing in the direction X, and that, and that, and okay. All right. The stand is fixed, so let me mount this on the stand. So coincidence between this axis and that axis, and coincidence between this plane and that plane. You don't have to select the bottom by flipping those arrows. I can manipulate it. And if it doesn't look good, you clear. In fact, when I say update here, it's not going to look good because these will both point to the same direction. They should be opposite. But let's check it out. There. You see that? Oh, it does look good. Okay. Yeah, that's fine. That's fine. Now, coincidence between this axis, that axis, and coincidence between this plane and that plane is going to be another revolute joint. They see now they don't look good. So double click on this last coincidence, that last coincidence, and flip the arrows. And now update. It's going to look nicer. Okay? Now let's bring in this fellow and put it in that hole. So coincidence between this axis and that axis, and pretty much it. Okay. So now I want to put this on that. Now we know that this ellipse is not going to go. Excuse me. Now we know that this ellipse is going to has to stay put in space. That being the case, what I can do is I can rigidly attach it to that. This paper clip means that this can be rigidly attached to that. And since the stand is not going anywhere, the path is not going to go anywhere either. So here, right there, you see that? Fixed together, that guy and this guy. So they're attached together. That doesn't move. This path doesn't move. Now I'm going to put this point on that path. So coincidence between this point and that path. And we say, okay, good. Let's check a few things. For example, on the move and manipulate, let's rotate about this axis. Make sure that this box is checked. Yeah, that's the way it should be, isn't it? So it looks good. You will see that looking good, working here, doesn't mean it's going to work when later on we go to the kinematics. So save everything. You'll see that, and there's a reason for it. We'll see. In these 3-4 problems that we have done, we didn't run into that situation, but we will now. Okay, so we go to start digital markup, DMU kinematics. Get the magic wand out. A new mechanism, mechanism 1, auto create, say okay. So let's see what joints are created. Okay. A revolute between link 1 and link 2. That's right here. Right there. Link 1, link 2. A revolute between stand and the link 1. That we know. A rigid between path and the stand. That's good. The stand doesn't go anywhere. The path doesn't go anywhere. A spherical between the vertical member and the path. Now, the spherical joint means that this point cannot go anywhere. So I don't want that. I have to delete this. This was generated because I wanted to bring the point and put it on that path. And I did not, once I did that, I did not deactivate or delete that constraint. So this has to go. Good. Okay. Now, let me actually undo this, Control Z. There is a reason I want to undo it. Let's try to delete it again. Right click, delete. I'm going to say don't delete the children. What that means is that don't delete the constraint that I put in there. Okay, because if I ever need it, I have to do it again. So I ask it not to delete the constraints that I put in the assembly design. Fine. Now the degree of freedom is 4. Okay. This point must travel along that path. It's a joint that you have to do manually. Look, not all the joints can be done with the magic wand. Just look through here. There is a joint called point curve joint. Point curve joint. You click on it. It says, okay, where is the curve? The curve is that path. Where is the point? The point is that point that I created at the bottom of this vertical member. If necessary, you can select it from the tree, or I did it. Now, remember, notice that there is a checkbox here, length driven. Let's not ignore that for a second. Close. Degree of freedom is 2. The question is, why is the degree of freedom 2? The issue is the cylinder, because this cylinder, this vertical member is a cylindrical joint. It has the ability to spin about its own axis, and we don't want to do that. Okay? So that cylindrical joint, we actually have to convert it to a prismatic joint. Okay? Prismatic joint. Up and down. Cannot spin. You have two choices. You can delete this. And make a prismatic joint. No problem. Or you can just completely delete this whole mechanism, go back to constraints, and say, for example, a vertical plane of this link and a vertical plane of, the vertical plane of this vertical member and the vertical plane of this link 2 stays at the same angle. That means this will not be able to spin about its axis. That means instead of cylindrical joint, a prismatic joint will be created. And when you use the magic wand, this is not going to be cylindrical, it's going to be prismatic. Now, if you go and look at several videos from previous years where I did this problem several times, most of the years I had done it just like the way I described. I completely got rid of this mechanism, went up there to the constraints and put a constraint, came back and did the magic wand. So please go ahead and do that. But here I'm going to do it differently. I'm going to say, okay, let me delete this and I'm going to turn it into a prismatic joint. Okay. I'm going to delete it. Gone. So I'm going to make a prismatic joint. Here's a prismatic joint. Okay. What do I have to do? Align. Align is axis of this, and I'm going to hide that, axis of that. Okay? Plane. Vertical plane of member, the member that I call vertical member. So for this, I'm going to select ZX. Okay, ZX. See that? This is the vertical member, ZX. Okay, and link to ZX. This will make that prismatic joint. Say okay. Right there. Prismatic joint. And the member is in hiding, so let me go get it for you. Because I hid it. Remember, I hid it. Excellent. Degree of freedom 1. I can make this point curve joint length driven. Here's the point curve joint. Length driven. And it goes between 0 and 300 millimeter. Obviously, the length of that path is 300 millimeter. Mechanism can be simulated. Can I do that manually? Here's the manually. You see that? Let me put it back. Let me put it back to 0. Good. Can I create a simulation? Sure. Insert. Put it all the way to the end. Insert. And change it to anything but 1. And then you can play it continuously. You can slow it down here. Okay, now there's no physics here. There's no physics. What I want to do is I want to say what is what the speed, for example, I can say what is the speed of this point at the bottom on the curve. So we say fine, stop it, rewind it, we say okay. Now I want to specify the velocity or the speed of this point on that curve. Remember how physics is brought into the picture. You're going to click on the f of x. Okay, this gives you all the junk associated with this mechanism, click on the mechanism. There's two things, time and that command. So you select that. That's the command. Add a formula equal to length equal to what speed do we want? So let's make it, I don't know, maybe 4 millimeters. 4 millimeters. Maybe look at the 20 millimeters underscore second times time. I remember the length of this thing, the length of this whole thing was about 300 millimeter. So it's going to be about 15 seconds probably to get this. So if I make this thing maybe 30, takes about 10 seconds. Okay. Uh, okay. So we say fine, assuming that there are no mistakes in the units and everything, we say fine, no complaints. We can do simulation with laws. Okay. If there's any sensors, we can plot it, create it. So let me go and make a sensor here. Close. Let me go and, for example, look at the, well, actually, you know what? We already have a point. We can plot the acceleration of that. Okay, so let's go ahead, acceleration of that point. Now remember, acceleration of that point is not zero. Just because the velocity is constant, speed is constant, acceleration is not necessarily zero because it's going along a path. So let's go ahead and do the sensor, speed, acceleration. The reference point is that same, reference product is that base, and the point selection is that point, the bottom of this. Okay, so we already created a speed acceleration sensor there. So we go simulation with laws, activate sensor, and let's say we want the speed of that point. So that magnitude, right? Magnitude is linear speed, or sorry, acceleration. Linear speed, we know what it is. It's going to be that 30. But let's actually ask for that too. Linear speed and linear acceleration. By the way, notice the units here or right now for linear speed is inch per second. Remember, because last week when I did these problems, I changed my speed to inch per second, and my currently my acceleration in meter per second squared. Please make sure that you submit your plots in the units that I'm asking for. In other words, if I ask for units of speed being in millimeter per second, which incidentally is going to be constant, it's going to be that 30 millimeter per second, and the acceleration millimeter per second squared, go change it, please. But I'm not going to do that. You are responsible for doing that yourself. So let's go plot, let's go run it over 10 seconds. Yeah, that should go at least almost one round. If I play this thing, I'll notice that nothing will happen. Oh, no, actually it did happen, right. uh, so let me move back. Let me rewind this thing. Move back here. I'll clear the history again. Let's play it again. I'm gonna make maybe the time a little bit more. I'll make this thing maybe 20. Okay, and play it. I did clear the history. That's good. Play it, and then graphics. So what you're going to get is although the units are not, may not be what I'm asking for, because right now, this is angular speed. I didn't want angular speed, I want linear speed. But you get the picture. If you should have selected linear speed. Linear speed, this is angular speed. That's why the unit is RPM actually, and you can change it. But anyway, so you are responsible for being able to generate plots of different units of different things versus time, different variables, customized plot, etc. So I'll just leave it to you to explore these things, and that's pretty much it for today. Oh, Do not forget to take a screen capture this. If it's on a test, then you have to screen capture it, because otherwise there's no way for me to know whether you have done it or not. So for example here, and then you go to a say Word document, PowerPoint, and then you paste it, and then you save it, file, save as, browse. In that folder, which was right here, week 4, activities, and it was this one, I believe. Yeah, my wrong plot. Do not give me all the plots that you can generate. Just give me the stuff that I've asked for. Now I say wrong plot because I really didn't want angular velocity versus time. So anyway, it's going to go into that folder, and if you check it, if you check that folder, hopefully we can find it there. Is it here? No. No. Yeah. It's my wrong plot. So when you submit this thing, I'll look at it. Are the units right? Can I read the scale? Can I read the units? Or is the thing that you gave me what I asked for? And based on that, I'm going to give you your part marks. All right, folks. Good luck.